So, hello everyone. So, today we are going to discuss the last lecture of this module, that is different type of controllers. So, if you remember the last lecture where we discussed the process dynamics. So, what is process dynamics? We discuss the change in the process variable with time, because we are dealing with the living system. That system itself is a dynamic. So, for that we need to understand the concept of degree of freedom, which gives the idea is what is the maximum number of variables that we can fix or minimum number of variables that is required to completely define a system. Then we discuss couple of example, continuous state tank reactor, how to get those mathematical equations, and one simple example we discuss, chemical mixing process. Then further we discuss, once you are having this developing the models, then you may have linear or nonlinear equations and how to solve it. So, we need to utilize different softwares and numerical methods to get the solution for that. So, in today's lecture, what we are going to discuss, what are different type of controllers, starting with proportional controller, proportional integral control, proportional derivative control, and combination of all three, proportional, integral, derivative control, and last one we will quickly discuss on-off control. So, before go ahead, let us quickly revisit this how the process control works. So, this was the same example which we discussed in the last lecture. So, there are two inlet and this is the outlet, and because of some changes in the here, we are going to make necessary process control by varying this W2 and X2. For that, what you need to do, first you need to measure these controlled variables. So, for that the composition analyzer slash transmitter measures. So, this is a AT, measures the exit composition and transmit it as electronic signal to the controller. So, this is your measuring device, and AC is the feedback controller. So, it is measuring here and transmitting the data to the controller. And now, controller compares the measured value, let us say XM, with the desired value or the set points and calculate the appropriate output signal P. Typically, P will be difference between set point and the measured variable, and electronic signal that is sent to the final control element. In this case, it is current to pressure transducer, where it is converted to an equivalent pneumatic signal that is compatible with pneumatically activated control valve, and this valve then it will open, and depending on that this stream 2 will be added in the system. So, what it says, you are having this control variable, you need to measure, that is a measuring instrument, and at the same time this measuring instrument we can say it is a sensor cum transmitter, it measures and transmit to the control, and the feedback control it compares with the set point, and then it transfer to final control element. In this case, the final control element was pneumatically activated control valve. So, it give a signal to this control valve, and finally the process control will work. So, it is the objective, the control objective is to keep tank exit composition X at a desired value, whatever the set point you want to set, by adjusting the W2, the flow rate of pure component A, because we are saying X2 as 1 via the control valve. So, in this way, if you know what is the objective, then you can design how the process control will work. So, we can now explain in a better way. So, you are having a process stream here. The flow rate of a process stream is measured. The first thing is you are having a flow transmitter, you measured it, then transmitted electronically to a flow controller, and now full flow controller is going to, the controller compares the measured value to the set point and take an appropriate corrective measure by calculating the controller output, transmitting it as an electronic signal to the control valve, and accordingly the control valve will open. So, basically the whole idea is to minimize the error, and error is defined as difference between the set point minus measured value. So, let us say this is a set point YSP and this is the input signal which is coming from the transmitter. The controller compares these two and then it passes the output signal P to the final control element. In this case, let us say it is a control valve. So, the error is set point minus measured value, and the whole objective here to reduce the error signal E to 0. Now, what are different type of controller which are applied for this purpose to minimize the error? They are proportional, proportional integral, proportional derivative, proportional integral derivative control, and on-off control. So, this we have already discussed. The error is defined as ET is the error signal is defined as set point minus measured value of controlled variable. Now, for the proportional control, what it says is the controller output is proportional to the error signal. So, it says PT, which is the controller output, is the proportional to the error signal ET, and the proportionality constant is the Kc, so it becomes Kc into ET, plus there is a steady state value, or we can say the bias value. What is the steady at steady state? What is the value of the P? So, this is the very simple equation for the proportional control. So, what is Kc? Kc is the proportionality constant that is defined as controller gain, and typically it is dimensionless, but depending on the unit of error or unit of your output, it can have the similar unit. Now, what are the key concept here? How it is going to work? First, the controller gain, that is the Kc, can be adjusted to make the controller output changes as sensitive as desired to deviations between set point and control variable. So, first thing is you can adjust the Kc value, and second thing is the sign of Kc value. It can work in a both the direction, whether controller output need to increase or it need to decrease in response to the error signal. So, it may happen, let us say if you are going for a pH adjustment. So, you need to decide whether you need to add acid or you need to add alkali. So, the Kc is important parameter for the proportional control. Many times this gain is not there, so it is also represented in terms of proportional band, and proportional band is Pb is inversely proportional to 1 upon Kc, or you can say it is 100% divided by the Kc. So, some controller have a proportional band setting instead of a controller gain, so that we can easily interchange among them. Now, how it will change? You just see this is the error and this is the output, and as I told, when error is 0 there is certain value of P, that is the steady state value. We write the P bar, or you can also write the PS, steady state value, and here the slope will be Kc. Kc will be the slope, the proportionality gain. Typically, you just see with respect to the error, you are going to have the kind of a linear response. But in actual case, you cannot have, you need to define the range of p. So, we set both lower and upper limit. So, we set a limit p minimum lower limit, p maximum upper limit, where it reaches to the saturation rather than just being a linear. So, this proportional control is going to work between these two limit of p, p minimum to p maximum. So, there are certain disadvantages. So, an inherent disadvantage of proportional controller is steady state error or offset occurs after a set point change or even after a sustained disturbance. So, there is a issue of offset that will always be there. It reaches to a new steady state value, but still that error will be there, because if you just see p is proportional to this steady state value plus the response. So, for that one option is one can add this integral control mode to facilitate the offset elimination that we will be discussing during this PI proportional integral control. So, in addition to that, there is one more term that is called transfer function. The transfer function, let us say this is GS is a transfer function. So, this is the ratio of outlet to the inlet, but you just see the S refers to the Laplace transform. So, why you need to go for Laplace transform? As we have discussed in the last lecture, many times we need to solve those differential equations, and Laplace transform is another way to easily solve those differential equations. Now, you just see, in order to derive a transfer function of an ideal proportional controller, we first define a deviation variable p dash t. What is, how much deviation is there? Is pt minus the steady state value ps, and if you put this in the first equation, that was pt as p bar plus kc into epsilon t. So, if I put these two values, so we will end up with p dash t equals kc into e bar t. So, one can take the Laplace transform and rearrange them. So, we get the kc as ps upon es. So, this is the, your outlet is the, here you can say p dash s, inlet is es. So, basically transfer function is converting this input to the output or the forcing function to response. Now, next controller is the integral controller. So, it says the controller output depends on the integral of error. So, it says Pt is proportional to integration of Et into dt, and here the proportionality constant we write as 1 upon tau I Et dt, and tau I is referred as integral time or the reset time. So, what is the advantage? As it is integrating the error, it eliminates the offset value. So, now it is possible to add this proportional and integrated integral control. So, it becomes Pt is p bar steady state value plus, in the case of proportional control it was kc into Et, in the case of integral control it is kc upon tau I 0 to t Et dt. So, one can take kc out here, and in this way we are having this proportional integral control. And if you just see its response here, so what you are getting, the first term is kc is coming from the proportional control, and kc upon tau I is coming from the integral control. So, in this way you just see with the time how response is changing, and we have taken the unit change in the input parameter or the error. This is the profile of the error, how this epsilon we have taken 1 for the unit step response. For one change in the error, how your output will change. So, it is saying you can see the response for both Kc as well as the Kc upon tau I with t. So, here there will be first increase due to proportional control, followed by linear increase due to integral control. And similarly, we can now define what is the transfer function Ps upon Es. This will be simply Kc 1 plus 1 upon tau I into S. So, it also has certain disadvantage, like it tends to produce oscillatory responses because this is an integration. So, it is produces the oscillatory response of the controlled variable. Of course, it minimizes the offset, but it takes long time due to this oscillatory response. Next is the derivative control. So, it says here the output will be proportional to the derivative of the error det upon dt, and if it is derivative means the function of derivative control action is to anticipate future behavior of the error signal by considering the rate of change. We are considering the rate of change. So, it is possible to have this anticipate the future behavior of error signal in the case of derivative control. And here the proportionality constant is the tau d, that is derivative time. So, it says the controller output is equals to nominal value p as long as error is constant. What does it mean? It means if det upon dt is 0, it means this pt will be equals to the p bar. So, it is going to have this nominal value of p all the time. Consequently, the derivative action is never used alone. So, what it says, it is always used in conjugation with proportional or proportional integral control. So, it will be either PD or it will be PID control. So, we can write now this, if it is a PD control, so P will be a function of Kc to error, this is coming from the proportional control, plus Kc tau d into d epsilon upon dt, it is coming from derivative control, plus P bar is a steady state value. And here again for one can write for the linear function, you can say Et as a step change a into t. So, we can write Pt as a kct plus this will be at. So, we will only get this a kc tau d plus here. So, what we are seeing here is now this value will be constant, the response from this derivative control will be constant, it will not change with time, but the response from the proportional control will change with time over here. So, similarly we can calculate the transfer function, this Ps upon Es will be Kc 1 plus tau d into S. So, we can see this response here. So, what it says is if you increase with change in, it says with change in the time, the first response will come from the derivative control, that is the a Kc tau d, then a into Kc, this will be the slope for the proportional control. So, this is the proportional control and this is a coming from the derivative control, and error we have taken a Et as a into t. So, in this way we just see how the response p value is changing with time in response to the error value. The next comes this PID control, where you are going to have this all three. So, now this PID, it can be in the parallel or it can also be in the series. There are possibility to have different combinations or different arrangement for the PID. So, in this case what happens, the PT will be first is coming from the proportional control, this is the derivative control, and this is the integral control, and this steady state value. Similarly, one can write the transfer function, this will be Kc 1 plus tau ds plus 1 upon tau is. So, in this way this PID control works. So, it is having the response of all three control system. So, in fact, if you just see the typical response, one is the when there is no control, this is how the control variable or deviation were there. Now, second is the proportional control. Once you are having the proportional control, it has controlled, there is a least deviation, but you just see always there will be a offset value. Next comes proportional integral control, third one. So, here what you are seeing is, of course, this offset has been minimized, but you just see the oscillatory behavior over here that comes from the integral control. Then fourth one is, you can just see, you can have this PID value, and here you just see it is reaching to the equilibrium much faster, and the offset is also not there in the case of PID control. So, the PID control is supposed to give the best response among all three control system, but of course at the same time it may be expensive as compared to the other controllers. Now, what are the feature of PID controller? So, let us say in the case of productivity, if poorly tuned PID loops, it can cause, let us say, oscillatory in the process parameter like pH and dissolved oxygen, which can stress the cell and ultimately lead to the lowering the yield. So, it says it affects the productivity. So, one need to have a better control of these process variables, so that the cells can grow and utilize your substrate to produce the desired metabolite. Second comes the quality. The stable control helps to maintain the critical quality attributes like, let us say, structure of your protein or glycosylation pattern. So, whatever biochemical features are expected in your metabolites, that are also affected by this inlet or the process variables, and this is very important, the reproducibility. If you are having consistent PID tuning across runs, it can improve the batch to batch consistency, which is vital for the regulatory compliances. In bioprocess, there are a lot of scope. You name any process variable that need to be controlled. For example, dissolved oxygen, pH, temperature, foam, these are part of upstream. In downstream, you can have chromatography, column temperature and flow. You can have filtration and ultrafiltration process. So, here I have listed very general. So, let us say in the case of DO control, the PID loop adjusts the aeration rate, it can adjust the agitation speed or oxygen enrichment to keep the DO level at the set point. Similarly, pH, it will ensure the addition of either acid or base to maintain the pH within tight limits. Similarly, temperature, it will ensure either heating or cooling is required. For anti-foam, it will trigger the anti-foam dosing if foaming is present. Similarly, in case of chromatography, it ensures the stable flow rate and temperature for consistent separation performance, and in the case of filtration it controls the pressure and the flow for the better performance, and also to prevent the membrane fouling and maintain the desired product yield. So, one more controller, that is the on-off control. So, if you remember, in the case of proportional control, if the gain value is very high, then what will happen? The valve will move to one extreme position to the other if process deviates only slightly from the set point. So, this is particularly on-off control. In this case, either it will be open or it will be closed. So, this is very sensitive action, is called on-off action, because the valve is either fully open or fully closed. And what is advantage here? The on-off controller are simple, inexpensive feedback controller that are commonly used not at the large scale, but as thermostat in the home heating system or in domestic refrigerator, because they are relatively inexpensive. They are also used in non-critical industrial applications such as some level of control loops and heating systems. So, for ideal on-off control, controller output has only two possible values that can be expressed mathematically as well. So, if error is greater than 0, automatically it will reach to the other extreme P max. If it is less than 0, it will reach to the another extreme, that is the P minimum value. You can see the response here. This is the error, and you just see value is still 0 without any deviation. Kc value is very high. So, response at the same time it can reach to the P maximum, and at the same time it can be to the P minimum. Now, what happens? The practical operation for such control is difficult. So, there is term comes dead band. So, in this range it works. So, in this dead band it is going to work. So, from here it will go to the P maximum here, and if it has to come down, it will come to the P minimum. So, there is certain this dead band, that is the actual case. So, particularly this it reduces the sensitivity to measurement noise, otherwise the valve will keep on opening and closing. Now, in bioprocess there are apart from disturbances, there are various manipulated variables. For example, in the case of pH, final control element can go for acid addition or the base addition. This in case of diesel oxygen, it can adjust the agitator RPM, air flow rate or oxygen enrichment. In case of temperature, it can go for the cooling jacket valve opening, heating jacket valve, or even temperature can be adjusted by the agitator RPM by ensuring the proper heat transfer. And foam, it can go for the anti-foam addition. Now, we can quickly summarize these basic control modes. Proportional, the output is proportional to the error, and it is a simple, fast, but it leaves the steady state offset. Integral, it is output is proportional to accumulated error over time. It eliminates offset, but it can cause oscillations. Derivative, it is output is proportional to rate of change of error, and it can anticipate future error. It can improve the stability, but it amplifies the noise because it can reach to a new steady state value. And PID control, it combines mode of balance between speed, accuracy as well as stability. It has the best feature among all other control modes. So, with this I will stop here. Thank you so much.